Welcome to Spaceverse, your portal to cosmic adventures. Our universe is a vast nursery where thousands of stars are born every single second. Somewhere in a distant corner of space, far from our own solar system, young stars are forming right now, wrapped in swirling clouds of gas and dust. But how exactly do these stars grow? And how do the planets around them begin to take shape? Thanks to the James Webb Space Telescope, astronomers are beginning to uncover the answers. Today, we're diving into the latest discovery that could reshape our understanding of how stars and planetary systems are born. For the first time, scientists have captured the most detailed images yet of mysterious winds of change, powerful streams of gas that help shape protoplanetary disks around young stars. These disks are essential for star growth and planet formation. And it turns out, a mechanism astronomers have theorized for decades may finally have direct evidence. Let's start from the beginning. When a star is born, it's not the blazing ball of fire you might imagine. At first, it's just a protostar, hidden deep inside a thick cocoon of gas and dust, the leftover material from the giant molecular cloud that collapsed to give birth to the star. Inside this swirling chaos, gravity pulls material inward, forming a spinning disk around the baby star. This disk, known as a protoplanetary disk, acts as a cosmic feeding ground. Dust and gas spiraled in, slowly nourishing the protostar, helping it grow into a full-fledged star capable of nuclear fusion. But here's where the mystery begins. According to physics, this rotating disk should have a problem: angular momentum. It's the same principle that keeps figure skaters spinning when they pull their arms in. Without losing some of that rotational momentum, the material in the disk can't fall onto the star. Instead, it should remain trapped, endlessly spinning around the protostar. Yet, clearly, stars do grow. Planets do form. So how does the disk shed enough momentum to allow this process to happen? For years, astronomers suspected that something must be pulling the brakes. Now, using the unprecedented power of JWST, astronomers may have finally found that missing piece: magnetically driven disk winds. A team led by Ilaria Pascucci from the University of Arizona's Lunar and Planetary Laboratory used JWST to look at 4 protoplanetary disk systems that appear edge-on from our vantage point here on Earth. Why edge-on? Because this orientation blocks the blinding glare of the central protostar, allowing JWST to see the winds and fine details in the surrounding disk material. What they found could change how we think about star and planet formation forever. Using JWST's near-infrared spectrograph, or NIRSPEC, astronomers tracked atoms and molecules moving through these young systems. JWST's unique sensitivity in the infrared allows it to penetrate thick clouds of dust, revealing what optical telescopes cannot. By watching how specific atoms, like hydrogen, move through these disks, the team mapped out cone-shaped winds blowing from the disk surfaces. Incredibly, these winds match the characteristics of a mechanism theorized for decades: magnetically driven winds, accelerated by the star's magnetic fields, pulling gas away from the disk and stripping angular momentum in the process. Our observations strongly suggest that we have obtained the first detailed images of the winds that can remove angular momentum and solve the long-standing problem of how stars and planetary systems form, said Pascucci. Think of it this way. These winds are like cosmic exhaust vents, allowing the disk to release excess spin energy so the star can continue feeding on the material that surrounds it. In fact, 2 different types of winds were detected, each with distinct roles in the life of the star. First, there are thermal winds caused by the intense radiation of the young star heating and pushing material outward from the disk's outer regions. These winds are relatively slow but steady, acting like a gentle but persistent breeze blowing away lighter gas from the system. Then there are the more mysterious X-winds. Named for their origin point near the X-shaped region where the disk meets the star's magnetic field, these winds are much faster, traveling at hundreds of miles per hour. They originate much closer to the protostar and are powered by the interaction between the star's rotation and its magnetic fields. X-winds are far more efficient at pulling material directly from the inner disk and flinging it into space. According to Tracy Beck from the Space Telescope Science Institute, Distinguishing between these types of winds is crucial to understanding how different processes affect star and planet formation. But JWST has provided something even more profound. Thanks to the telescope's high resolution and the use of the Integral Field Unit IFU on NurseSpec, astronomers were able to construct detailed 3D models of these wind structures. What they found were onion-like layers of gas surrounding a central jet. This jet, a narrow beam of particles, is encased within a wider cone of wind material, each layer originating from different regions of the protoplanetary disk. As you move outward from the star, the layers change, indicating how material is progressively lifted off the disk's surface at different distances. In all 4 protoplanetary disks studied, the winds formed cones with noticeable hollow cores, like empty tunnels running along the system's axis. These core holes are believed to be where material from the disk is funneled directly onto the star, while the surrounding cone is where the winds carry away the excess angular momentum. The discovery of these cone structures could explain how stars manage to continue accreting material over millions of years, while simultaneously preventing the disk from spiraling completely inward. But how common are these structures? According to Pascucci, that's the next big question. While these findings are significant, they're based on just 4 systems. Are these magnetically driven disk winds a universal feature of star formation? Or are they unique to certain types of stars or environments? We believe they could be common, but with 4 objects, it's a bit difficult to say, Pascucci noted. We want to get a larger sample with JWST, and then also see if we can detect changes in these winds as stars assemble and planets form. The implications extend beyond stellar physics. Understanding how these winds behave could unlock new insights into planet formation itself. Why? Because the disk isn't just feeding the star. It's also the birthplace of planets. Planets form from the leftover material in these disks, the dust grains that collide and stick together, forming larger bodies over time. The winds detected by JWST could be influencing how and where this planet-building material is distributed. By controlling the disk structure and lifespan, magnetically driven winds may directly impact whether a young star forms a family of planets or ends up barren. And this research goes even further. According to estimates, around 3,000 new stars are born every second across the observable universe. That means that every second, 3,000 stellar nurseries light up, each with their own protoplanetary disks, their own swirling winds, and their own potential for planetary systems like ours. What JWST has captured isn't just an isolated phenomenon. It's a fundamental process happening all across the cosmos. By observing these nearby protoplanetary disks, astronomers are essentially looking back in time to a period about 4.6 billion years ago, when our own sun was a protostar wrapped in a similar disk of gas and dust. This is what our solar system once looked like. These winds of change, now visible thanks to JWST, could have shaped not just the formation of the sun, but also the architecture of the planets, including Earth. For decades, scientists have built models to simulate how stars and planets form. But models rely on assumptions. Thanks to these observations, astronomers now have direct evidence of processes that once seemed impossible to observe. And this is only the beginning. JWST's infrared eyes have opened a window into the dusty realms where stars and planets are forged. With its sensitivity and resolution, astronomers plan to survey dozens more protoplanetary disks, searching for similar winds, hollow core cones, and layers of gas flow. Future studies could reveal how these winds evolve over time. Do they slow down as the star grows? Do they disappear as planets begin to form? Or are they present throughout the entire process, subtly guiding the formation of new worlds? Answering these questions could help solve one of astronomy's biggest mysteries. Why do planetary systems form so differently from one another? Some stars form tightly packed planetary families. Others seem to have no planets at all. Perhaps these early winds blowing through the dusty disks hold the secret. And JWST, launched in 2021 after decades of planning and billions of dollars of investment, is proving once again why it's the most powerful space observatory in human history. By peering into the hearts of stellar nurseries, it's showing us the cosmic dance that gave birth to stars, planets, and ultimately life itself. The universe is a story still being written, and with each new discovery, telescopes like JWST are helping us read the next chapter. If you found this exploration of stellar formation and protoplanetary winds fascinating, don't forget to like this video, subscribe to Spaceverse, and click the notification bell so you never miss the latest cosmic discoveries. From the birth of stars to the creation of planets, we'll be here to explore every step of the cosmic journey.